In this video, we are going to continue to look at Activity 3C, Hess's Law and Enthalpy of Formation Practice. And we are starting off this video with problem number 4. So problem number 4 says the heats of combustion of carbon, H2, and CH4 at 298 Kelvin and 1 atm, which is standard temperature and pressure, are respectively negative 393 kilojoules per mole, negative 286 kilojoules per mole, and negative 892 kilojoules per mole. What is the enthalpy of formation for CH4? And then it tells us that the three combustion reactions are these three reactions, and it also rewrites these values for us in a table format to make it a little easier to look at. Oh, and then it's saying the reaction that we're looking for, the enthalpy of formation reaction for CH4, is C plus 2H2 gives us CH4, which would be the formation of CH4. And so you might be saying, well, why can't we just get an enthalpy value for this reaction? And that's a valid question, but some chemical reactions are really hard to actually carry out. And so it's hard to measure the enthalpies for the specific reaction, but we can measure the enthalpies of other reactions and then use Hess's law to figure out the enthalpy for our target reaction. So Hess's law says that if we can add up multiple other reactions to equal a target reaction, then the enthalpy of our target reaction, which in this case is this reaction right here, is going to be the sum of the enthalpy values of the reactions that we added up. So in Hess's law problems, you'll generally be given a list of reactions with their enthalpy values, and then you'll be given a different target reaction. So here's our target reaction, and these are the three reactions that we have to work with. So we need to manipulate these equations so that when we add them all up, we end up with just this reaction left over. And so what I like to do is I start by looking for the substances that are in my target reaction that only appear once out of all of the reactions that I have to work with. So if I'm looking through, I see that oxygen appears several times, so I'm going to worry about that last. I see that H2O appears more than once, so I'm not going to worry about that right away. And I see that CO2 also appears more than once, so I'm not worried about that either. But then looking, I see that carbon right here, I need to have carbon on the reactant side of my target reaction, and I see that carbon, out of all three reactions, it only appears right here in reaction A. And I need to have one carbon on the reactant side of my target reaction. So that tells me that I want to keep this reaction exactly as is, so I can keep that carbon in the correct place. So I'm going to go ahead and write reaction A, and I always like to keep them labeled to kind of stay organized here. So I'm going to rewrite that. Carbon plus O2 gives me CO2. And because I didn't manipulate this reaction at all, the delta H value doesn't need to be changed at all. So my delta H is still negative 393 kilojoules. And then I'm going to kind of check that one off. So I know that I've already used that one once. And it's most likely that I'm going to use each of these reactions one time to this problem. Looking through the problem again, I also noticed that I need CH4 on my product side of my target reaction, and CH4 only appears once. It only appears in reaction C, and it's in fact on the wrong side of reaction C. So I only have one opportunity to fix that. I need to do a manipulation of reaction C that's going to put CH4 on the product side, and I need to have one CH4 on the product side. So if I just flip this equation around, that'll do the trick, and then I'll have one CH4 molecule on my product side. So I'm going to write reaction C next, and I'm going to make the products the reactants, and I'm going to make the reactants the products. So I'm just going to flip this around. So I'm going to put CO2 plus 2H2O yields CH4 plus 2O2. And so because I flipped my reaction around, I made the reactants the products and the products reactants. I also need to reverse the sign of the delta H value because this original reaction had a negative value, which means it was exothermic, but if I do the reaction in the opposite direction, my reaction is now going to be endothermic. So instead of negative 892, the delta H is now positive 892 kilojoules. And I'm going to check that one off as well. So now I'm going to go ahead and cancel some things out. I notice that I have CO2 on both sides of my reaction. So if I have a CO2 on the reactant side and a CO2 on the product side, those are going to end up canceling out. So I'm going to go ahead and cross those out so I can kind of look at what I have left here. I also noticed that I have one O2 on the reactant side and two O2s on the product side. So I can cancel one of the O2s with one of the O2s here. So I'm going to cross this one out completely. And then instead of two O2s, now I'm just going to have one O2 left here. So I'm going to cross out that coefficient of 2. So I'll put X's through these to know that they're completely gone, and I'll put an X through that 2 there. We just have one O2 molecule left. And then carbon, water, and CH4 are still here. So I have one more reaction left to play with here. And I noticed that I haven't done anything with hydrogen. So I've dealt with my carbon, I have that on the right side. I've dealt with my CH4, I have that on the product side. But I still need to have two hydrogens on my, two H2 molecules on my reactant side. And right now I don't have any. So I need to make this reaction work for me so that I'll end up with two H2 molecules on my reactant side. So H2 is already on the correct side of this chemical equation, but I don't have the correct number of H2 molecules. So in order to get the correct number, I'm going to multiply reaction B by 2. I'm going to multiply the whole thing by 2. So it's just like algebra. If I do something to one side of the reaction, I do it to the other. So I'm just going to multiply the whole thing by 2. So instead of one H2, I'm now going to have two H2s. Instead of half of an O2, I'm now going to have one whole O2. And then I'm going to have two H2Os. And since I multiplied my reaction by 2, I also need to multiply my delta H value by 2. So I'm going to put 2 times negative 286 kilojoules. And I'll figure out what that number is after I finish doing the problem. So now, hopefully, everything will cancel out correctly, so I'll be left with just my target reaction left. So we need to double check to make sure that is the case. So my O2 that I have left over here will cancel out with the O2 that I now have on the reactant side. So I'll put an X through that and an X through that O2. These two H2Os on the product side will cancel with these two H2Os on the reactant side. So those cancel out. And now I am left with carbon on the reactant side, two H2s on the reactant side. So carbon plus 2H2 is left on the reactant side. And on my product side, I'm just left with CH4. So checking, I want to check to make sure that does match my target reaction. So C plus 2H2 yields CH4. C plus 2H2 yields CH4. So that is perfect. So I have this totally correct. So now all that's left is to find the delta H for this reaction. And all I need to do to find that delta H is to add up all of the delta H's for the individual reactions. So I'm going to grab my calculator, and I'm going to pay careful attention to my negatives and positives here. I'm going to do 2 times 286. So that gives me negative 572 kilojoules. So now I'm going to do negative 393 plus 892, and then minus 572. And that gives me negative 73 kilojoules. So my delta H for this whole reaction is negative 73 kilojoules. I'll move my calculator. I'm going to box in this answer. And then we are done. So in number 5, the problem is written a lot more simply. It just says, from the following data, gives us our 3 reactions with their enthalpy values, and then says calculate the enthalpy change for the reaction, this one. So this makes it easy. We know that this is our target reaction. This is what we are trying to get to, and we have these 3 reactions to work with. So I'm going to start by looking for things that only appear once, and immediately I see that N2O3 only appears in the first reaction, and it's right now it's on the product side, and we need it to be on the reactant side. So I'm going to start out by flipping reaction A around, and so we'll have N2O3 yielding N2 plus 3/2 O2. And since I flipped that reaction around, I'm going to reverse the sign of my delta H value. So I'm going to make that negative 83.7 kilojoules. So I took care of reaction A. Now looking at my next thing, I need NO, nitrogen monoxide, to be on the product side of my reaction. And I need one NO molecule. And I see that NO only appears in reaction B. It doesn't appear in reaction C. And in reaction B, we have two NO molecules, and we only need one NO molecule in our final reaction. So I am going to need to divide reaction B by 2. Or you can think of it as multiplying it by 1/2. Either way, whichever is easier for you. But I'm going to take reaction B. And I'm going to keep NO on this side, so I'm not going to reverse the reaction, but I am going to divide everything by 2. So instead of having 1 N2 and 1 O2, I'm going to have half an N2 plus half an O2. And that will yield 1 NO molecule. So 1 NO molecule. And since I have the reaction, I also need to half the delta H value. So my delta H value, I'm going to divide it by 2. So 180.4 kilojoules divided by 2, and we'll do that calculation at the end. Okay, and then I've used reaction A and reaction B, so now in reaction C, I see that the thing that only appears in reaction C is this NO2 molecule, and we need that NO2 molecule on the product side of our target reaction. So that NO2, we have one NO2 molecule in our target reaction, and there's one in reaction C, and it's already on the correct side of the equation, so I don't need to manipulate reaction C at all. I'm just going to rewrite it as 1/2 N2 plus O2 gives us NO2. And since I didn't do anything to the reaction, I'm also not going to do anything to the delta H, so it's going to stay 33.2 kilojoules. Alright, so we've used all three reactions, so now we have to hope that everything cancels out properly. And we are going to double check this. So I can look at my reaction. I see that I have 3/2 O2 up here, and I have 1/2 and 1 O2 down here. So 3/2 is the same as 1 and 1/2 O2s, so 1 and 1/2 O2s cancels out the 1.5 O2s up here. So since they're on opposite sides, all the O2s cancel out. Okay, now I have N2 on my product side. I have one N2 molecule, and I have a 1/2 N2 and a 1/2 N2 here. So a 1/2 plus a 1/2 equals 1 whole N2. So these two here cancel out with this one over here. So I'm going to X those out. The N2s cancel out. Now I have N2O3 on my reactant side, and I have NO and NO2 on my product side. So I'm going to box those in. None of these are going to cancel out. So now I'm just going to rewrite these out. N2O3. That's the only thing on my reactant side, so I don't need an arrow, I don't need a plus sign, I just need an arrow. Gives me NO and NO2. And I'm going to double check that this is indeed the same, and this is the same reaction as our target reaction. So all we have left to do is to add up our delta H values to find the delta H of our target reaction. So we're going to grab our calculator. First we'll do the 180.4 divided by 2, which gives us 90.2 kilojoules. And now we'll just add all of these up. So we have negative 83.7 plus 90.2 plus 33.2. And that gives us 39.7. So delta H is equal to 39.7 kilojoules. And we will box that answer in. In this problem, number 6, we are going to determine the enthalpy of the following reaction using the provided data. So once again, this is a Hess's law problem. We have several reactions with given enthalpy values, and we're working to find the enthalpy of our target reaction, which is right down here. So the first thing that I notice is the things that only appear once. And also, I want to just draw your attention to the fact that all these substances look very similar. All these equations seem to have iron in it with oxygen. I have FeO, and I have Fe3O4, and I have Fe2O3. So this can be very confusing, so we have to look very carefully at our equations to make sure we are correctly distinguishing the differences between the substances. So, looking at this, in my target equation, I have both Fe2O3 and I have Fe3O4. So I'm going to find these in my equations first. So I see that Fe2O3 is in reaction A, and it's already on the correct side of the equation. But Fe3O4 in reaction B is not on the correct side of the equation. So I'm going to make sure that I manipulate these two equations so that I get those two things on the correct side. So let's start there. It doesn't really matter which one you start with. I'm going to just start with A because A, B, C, but it doesn't really matter. You can do B first. So let's start with A. And Fe2O3, we need to have 3 of them in our target equation in the end. And Fe2O3 only appears right here. So we need to make sure that we multiply this equation by 3 so that we end up with 3 Fe2O3s on the reactant side. So I'm going to take this equation, I'm going to multiply the whole thing by 3. So Fe2O3, I'm going to get 3 of those, 3 Fe2O3s, and then I will have 9 COs, and then that is going to yield 2 times 3, 6 Fe's, and 9 CO2s. And you might have noticed that I did not write the state symbols here, and in this case I don't really need to because there are not different states of Fe2O3 and there are not different states of CO. So CO is all in gas, and Fe2O3 is all solids. But if you, for instance, had gaseous carbon monoxide and liquid carbon monoxide, then you would need to keep the state symbols and pay careful attention to making sure that you were canceling out the correct state of matter, the substance with the correct state of matter. But in this case, it's not really necessary to carry through the state symbols, so I'm just now going to put my delta H value. Since I've multiplied the equation by 3, I also need to multiply my delta H value by 3. So 3 times negative 23.44 kilojoules. So we've taken care of reaction A, so I'm going to check that one off. Moving to reaction B, we said we need to make sure we end up with Fe3O4 on the product side, and we also need to multiply the reaction by 2, so we end up with 2 Fe3O4s. So we're going to flip this equation around, and we're going to multiply it by 2. So that's 2 manipulations. So let's flip it around first, and then multiply it by 2. So I'm going to skip writing the coefficients for now. We'll come back and fill those in. So FeO plus CO2 is now going to yield Fe3O4 and CO. Okay, and now we need to multiply everything by 2. So 3 times 2 is going to give me 6 FeOs. 2 times 1 CO2 is going to give me 2 CO2s. 2 times 1 is going to give me 2 Fe3O4s. And then 2 times 1 will give me 2 COs. So since we flipped the equation and we multiplied it by 2, we need to change the sign and we need to multiply by 2. So I'm going to do 2, and then we'll make this a negative 21.79. Negative 21.79 kilojoules. Okay, so that takes care of equation letter B. So now I'm going to go through and see what cancels, because I can already see that I'm going to have some things canceling out here. So 2 CO2s are going to cancel out 2 of these CO2s. So I'm going to cross this one out completely. And instead of having 9 of these, now we just have 7 CO2s left. And then 2 of the carbon monoxides are going to cancel some of the carbon monoxide over here. So I'm going to have 7 carbon monoxides left. And now I have Fe2O3, Fe3O4, those don't cancel. iron and iron oxide. Those don't cancel either. Okay, so let's look at our final equation. So in our final equation, we have iron, which we don't want in our target equation. We have carbon dioxide, which we want 1 of in our final equation, but we already have 7 of them. We have iron oxide, which we don't want in our target equation, and we have carbon monoxide, which we want 1 of on the reactant side, but we actually already have 7 of those too. So there's actually nothing else that we want in our final equation. But, as we've said, we have too many carbon monoxides, too many carbon dioxides, and we also have this iron and this iron oxide that we need to make sure we get rid of. So this last equation, the use of this last equation is to make sure that things that we don't want in our target equation cancel out. So I want to make sure that all 6 of these irons cancel out. So I'm just going to focus on that, and I'm going to manipulate this equation to make sure that all 6 irons cancel out, which means I need to have 6 irons on my reactant side. So I don't need to switch the sign on this. I don't need to flip the equation around, but I do need to multiply the whole thing by 6 so that I end up with 6 irons on my reactant side to cancel out the 6 irons on my product side. So we're going to do 6 Fe plus 6 CO2. Multiplying all these by 6 gives us 6 FeOs and 6 COs. And if you just focus on one thing that you need to fix, generally speaking, in Hess's law problems, the rest will work out in the end. So we're hoping that will happen here, and if not, we'll go back and make some edits to our strategy. But let's go ahead and write our delta H value. We just need to take this delta H value and multiply it by 6. So 6 times negative 10.94 kilojoules. So now let's hope that everything cancels out correctly. So we know our 6 irons should cancel out. 6 irons cancels with these 6 irons. Our 6 FeOs on our product side will cancel out these FeOs over here. 6 FeOs cancels with 6 FeOs. Our 6 CO2s here will cancel all but 1 of the carbon dioxides over here. So we'll cross out these 6 and we'll cross out the 7, so we just have 1 CO2 left. And then our 6 carbon monoxides will cancel out 6 of the 7 carbon monoxides over here. So we'll cross that one out completely and cross out the coefficient there. So now we're left with CO2 over here, CO over here. Fe2O3, Fe3O4, so those don't cancel, so we're going to be left with those ones as well. So let's just rewrite this. Let's write our reactants. 3 Fe2O3 plus CO gives us 2 Fe3O4 plus CO2. Let's hope that matches up with our target reaction. 3 Fe2O3 plus CO gives us Fe3O4, 2 of those, plus CO2. So that does match up. It worked out nicely. So now all we need to do is add up all of our delta H values to get our delta H of our target reaction. So I'm going to move that over a little bit. I'm also going to move this up. So let's go ahead and do this in our calculator. Move that so we can actually see it. So we'll do 3 times negative 23.44, whoops, 2 times negative 21.79, and then 6 times negative 10.94. And then I'm going to take all these values and add them up. Plus that one. Oh, I need to open some parentheses though. Let's keep going, go over in my calculator, open parentheses, enter, close parentheses, hit enter, and I got negative 179.54 kilojoules. And I will box that in as my final answer. So our final problem here says, what is the standard enthalpy of reaction for the reduction of iron 2 oxide by carbon monoxide? And it gives us the equation up here, and then it gives us our 3 reactions with known enthalpy values to work with. So here's our target equation. I'm going to go ahead and box that in. Okay, and we need to start by looking at these reactions and finding things that only appear once. So FeO, let's look through. FeO only appears right here. So I'm going to start by working with equation C because FeO only appears in equation C, and I need to make sure that I have one FeO on my reactant side of the equation. So I'm going to take equation C, and we are going to flip the equation around and divide by 3. So we're going to have FeO, and let's double check to make sure everything is in the same state of matter. Iron solid, carbon monoxide gas always, FeO solid. Okay, so everything looks like it's all in the same state of matter, so I can skip writing that symbol. So I'm just going to put FeO plus CO2 gives us Fe3O4 plus CO. So I flipped it around. Now I need to divide everything by 3. So instead of 3 FeOs, I'm now just going to have 1 FeO. Instead of 1 carbon dioxide, I'm now going to have 1/3 of a carbon dioxide. Instead of 1 Fe3O4, I'm going to have 1/3 of that. Instead of 1 CO2, I will also have 1/3 of that. And now my delta H values, since I flipped the equation and divided by 3, I need to do the same thing to delta H. I'm going to change the sign to a negative sign, negative 21.79 kilojoules, and I'm going to divide by 3. And so that'll give me a new delta H value. So we used reaction C. Now let's keep looking for things that only appear once. So carbon monoxide appears here, and it appears here. So let's not worry about that one yet. Moving on to iron. Let's see, iron only appears right here in reaction B. So let's work with that next. We need to make sure that we have 1 iron on the product side of our equation. So currently, iron's on the right side of the equation, but we have 2 of them. So we need to divide reaction B by 2 so that we get what we need in our target equation. So we'll take reaction B, and we'll keep it the same, except we're going to divide everything by 2. So instead of 1 Fe2O3, I'll have 1/2 of an Fe2O3. Instead of 3 COs, I will have 3/2 of a CO. Instead of 2 Fe's, I will have 1 Fe. That one's the easy one. And then instead of 3 CO2s, I'll have 3 divided by 2 CO2s, 3/2 CO2s. So since we just divided everything by 2, we need to divide our delta H value by 2. Delta H equals negative 23.44 kilojoules divided by 2. And we'll find that answer later. Okay, so we're starting to get a whole lot of fractions going on here. And it bothers me because I have thirds up here and halves down here. So I'm not going to have any idea what cancels with what. I know that I have carbon monoxide over here and carbon monoxide over there, but in order to cancel out some carbon monoxides, I need to have a common denominator on my fractions. So I'm going to go ahead and I am going to convert the thirds and the halves to their lowest common denominator. And the least common denominator between a third and a half is going to be 6. So 2 times 3 gives me 6. So something out of 6 is going to be my least common denominator. So 1/3, if I convert that to sixths, let's do 1/3 equals what over 6, if you don't remember how to do this. So we're going to have 3, cross multiply, get 3x equals 6. If we divide by 3, that gives us 2. So 1/3 is equal to 2/6. And then 1/3 and 1/3, those are also going to be equal to 2/6. So I have 2/6 of everything up here. Now I just need to figure out my fractions down here. 1/2 is an easy one. 1/2 is going to be equal to 3 out of 6. 3/2, now you might need to do some math to figure that out. 3/2 equals what over 6? So let's cross multiply. 6 times 3 is 18 equals 2x, so divide by 2, x equals 9. So 3/2 equals 9 over 6. So we'll put 9 over 6 there. And then this 3/2 also will equal 9 over 6. So now that I have a common denominator, I can see that some of these carbon monoxides and some of these carbon dioxides are going to cancel out. So 2/6 will cancel 2 of the 6ths down here. So I'm going to cross this one out completely. And then instead of having 9/6, 9 minus 2 gives me 7/6 that are left. So now I have 7/6 down here. This 2/6 will cancel some of these 9/6 of my CO2, so I'm going to cross this whole one out. And now I'm going to have 7/6 CO2 down here. And now I have Fe3O4 and Fe2O3, and I can't really do anything with those right now. And then I have FeO, which I know I wanted, and Fe, which I also know I wanted. So now we have reaction A left to work with. So whatever we do to reaction A, we want to make sure that we cancel out things that we don't want. So we don't want these 2/6 Fe3O4. So we need to make sure that that does cancel out with our final reaction. So with this final reaction, Fe3O4 is on the product side. And I want to make sure that this cancels out. So I need Fe3O4 on the reactant side. And I need 2/6 Fe3O4, not 2 Fe3O4s. So in order to get 2/6 of an Fe3O4, I'm going to divide the whole thing by 6. And I'm going to flip my equation around. So take reaction A, we're going to flip it around. So Fe3O4 plus CO2 gives us Fe2O3 plus CO. And then I'm also going to divide all of my coefficients by 6. So instead of 2, I'm going to have 2 divided by 6, so 2/6. Instead of CO2, I'm going to have 1/6 of a CO2. Instead of 3 Fe2O3s, I'm going to have 3/6 Fe2O3. And instead of 1 carbon monoxide, I'm going to have 1/6 of a carbon monoxide. So now we need to change our delta H value. So we flipped the reaction around. We need to reverse the sign, make this a positive 48.26. And then we also need to divide by 6. So that should give us our final delta H value in a second. So I'm going to get a third color here because we've kind of gone a little chaotic with the fractions. So let's look at what we have left. So these have already canceled. The ones I'm Xing out in big blue, those have already canceled. So now we have 2/6 Fe3O4. We'll cancel these 2/6 Fe3O4. So let's cancel those out. Okay. We have 1/6 of a CO2 here, and we have 7/6 of a CO2 here. So this 1/6 is going to cancel one of the 6ths up here. So if we cancel one of them, we're going to be left with 6/6, which is the same thing as 1. So I'm just going to cross this out, and we'll just be left with one CO2 molecule. So I'm going to box that one in, and we'll cross that one out. Okay, it's getting a little simpler in here. The 3/6 Fe2O3 will cancel the 3/6 Fe2O3 up here. Before I cross those out, they cancel out. And then the 1/6 CO will cancel one of the 6ths of the CO up here. So we're going to end up with 6/6, which is the same as 1. So we'll just cross out the coefficients. We're left with just one CO, and this one cancels out. And then finally, we're just left with this iron and this iron oxide, which neither of those are going to cancel out, so we'll just box those in. Let's write out what we have left. So on our reactant side, we have FeO plus CO. And on our product side, we have Fe plus CO2. So let's double check. FeO, FeO, CO, CO, Fe, Fe, CO2, CO2. So it worked out perfectly. This was a whole lot of fractions and a whole lot of mess, but it did work out nicely in the end. And Hess's law problems are often like this. So now all that's left is to add up all of our delta H values. So move this up a little bit, and let's grab a calculator. Okay, so we have negative 21.79 divided by 3. We have negative 23.44 divided by 2. And we have positive 48.26 divided by 6. So then we're going to take those values and add them up. Close parentheses plus that one right there. And that gets us negative 10.94. So our delta H value is equal to negative 10.94 kilojoules. A whole lot of work, but we made it through to the end. Hess's law problems are a lot of problem solving, but in the end they do work out nicely, and it is somewhat satisfying